In the previous video, we developed the two equations which are both necessary and sufficient for the equilibrium of a rigid body. If a body is subjected to a system of forces in the xy plane, then the forces can be resolved into their x and y components. When in equilibrium, the net force and net moment acting on the body is zero. This 2D condition can be represented by the three scalar equations. Here sigma fx and sigma fy represent respectively the algebraic sum of the x and y components of all the forces acting on the body. And sigma m0 represents the algebraic sum of the couple moments and the moments of all the force components about the z-axis, which is perpendicular to the xy plane and passes through the arbitrary point O. Please note that these equations are the ones most commonly used for solving 2D equilibrium problems. The solution to some equilibrium problems can be simplified if we recognize members that are subjected to forces at only 2 points, for example at points A and B. If we apply the equations of equilibrium to such a member, we can quickly determine that the resultant forces at A and B must be equal in magnitude and act in the opposite directions along the line joining points A and B. In the cases above, members AB can be considered as two force members, provided that their weight is neglected. This fact simplifies the equilibrium analysis of some rigid bodies, since the direction of the resultant force at A and B are thus known. If a member is subjected to only three forces, it is called a three-force member. Moment equilibrium can be satisfied only if there are three forces form a concurrent or parallel force system. To illustrate, consider the member subjected to the three forces. If the line of action F1 and F2 intersect at point O, then the line of action of F3 must also pass through point O, so that the force is satisfied sigma m0 equal to 0. Is a special case. If the three forces are all parallel, the location of the point of intersection O will approach infinity. For solving 2D equilibrium problems, following steps must be considered. If not given, establish a suitable xy coordinate system. Draw a free body diagram of the object under analysis. Apply the three equations of equilibriums to solve for the unknowns. It is also important to note that if there are more unknowns than the number of independent equations, then we have statistically indeterminate situation. We cannot solve these problems using just statics. The order in which we apply equations may affect the simplicity of the solution. For example, if we have two unknown vertical forces and one unknown horizontal force, then solving sigma fx equal to 0 first allows us to find the horizontal unknown quickly. If the answer for an unknown comes out as a negative number, then the direction sense of the unknown force is opposite to that assumed when starting the problem. Okay, now considering this example, the 4 kN load at B of the beam is supported by pins at A and C. To find the support reactions at A and C, we need to take following steps. Put the x and y axis in the horizontal and vertical direction respectively. Determine if there are any two force members. Draw a complete free body diagram. Apply the equation of equilibrium to solve for the unknowns. Note that upon recognizing CD as a two-force member, the number of unknowns at C are reduced from 2 to 1. Now draw the free body diagram and apply the equation of equilibrium. The moment equation of equilibrium yields Fc 11.3 kN. Then applying the equation of equilibrium in the x direction gives the reaction Ax minus 8 kN. Similarly, the reaction in the y direction at A is minus 4 kN. Note that the negative signs means that the reactions have the opposite direction to that shown on free body diagram. Thanks for watching.